Hello everyone, and welcome to a very special live mission briefing for the James Webb Space Telescope. But what is the James Webb Space Telescope, and how is it getting to space? And what do we hope the telescope might see? Well, that is what this mission briefing is for, to find all of that out with the help of some special guests and with the help of your questions. Hello, my name is Greg. I am producing and hosting today's mission briefing, and I'm coming to you live from the Rutherford Appleton Laboratory in Oxfordshire in the UK. I am inside a place called Royal Space. It's the UK's national space laboratory. Loads of awesome stuff happens here, I tell you. This place is amazing. Check this out on the wide camera. Look at this place. It's incredible. Give a wave, everybody. Now look, it's also quite a noisy place. Inside the rooms around me, actual spacecraft are tested before they go into space. And I'm going to show you how noisy it is. Let's turn the noise filter off, can we, Owen? Yes? Yeah, you see, it's a little bit loud in here, so I might sound a bit funny. We'll put the noise filter back on. Hopefully that sounds a bit better. Okay, let's come back to me here. Hello, hope you can hear me. So, later on, one of our special guests, TV and YouTube's Maddie Moate, will be taking us inside the awesome test lab that is behind me. And if you are watching live right now, then please do put any questions you have in the live chat. Also, let me know your name and where you're watching as well, so I can give you a shout out. And if you're watching this back after the live, hello, you are very welcome too. There is loads on the way for you. I'm going to be discovering what a space telescope is and how it works when I'm joined by some of the scientists and engineers from all over the UK who helped build the James Webb Space Telescope and who get to use it when it's in space. I'll also be hearing about the launch when I'm going to be joined by someone from the European Space Agency later. Plus there's going to be facts, fun, some experiments you can try yourself, and a quiz. That is all coming up. Let's do some quick hellos to some of you watching live. Hello to Ken and Glenn and Jimmy and Ben and so many of you watching live. Keep the chats coming. I'm going to pick up as more of them as possibly can. Let's do some quick hellos to you a bit later. And if you are watching back, I am going to put, after this live, some chapter markers into the live, into the description below, and then you can easily click on them and jump to whichever bit you want to watch. So if you're watching back, have a look in the video description and you can jump to any bit of this video. A huge thank you before we start to the folks who have supported today's show: the Science and Technology Facilities Council, STFC, the James Webb Space Telescope UK team, and also the UK Space Agency. Thank you all. On then, with the mission briefing, what on earth is the James Webb Space Telescope? Or should that be more, what in space is it? Well, this is the James Webb Space Telescope. Let me bring up a picture of it. There it is. But how is that a space telescope? We call it Webb, by the way, for short. And like the name suggests, it is a telescope in space. In fact, it is going to be the largest, most powerful telescope that we will have ever launched into space. And today we're going to find out what it is and what it will do. But Webb is not in space yet. Right now, on Saturday, the 18th of December, a few minutes past 11, Webb is actually here. It's on the top of a rocket. So it's sat on the top of a rocket. They're about to put a casing around the top of it called the fairing, and it's almost ready to be launched into space. Now, if you're watching this mission briefing back a few weeks or a few months after the launch, and Webb is indeed up there right now, then I am very jealous because you will have seen the launch. But where is this rocket? Where is Webb right now? Well, it's in a place called French Guiana, here on the northeast coast of South America. It's at Europe's spaceport at the Guiana Space Center in Kourou. In a few days, it'll be taken out onto the launch pad and blasted into space. More on that later, though, when I'm going to be joined by a special guest from the European Space Agency who is going to tell us what will happen during the launch. I think we should get to know Webb a little bit better first, though, shall we? I'm going to start with some of your questions. One from Isla Grace, I'm going to start with, who's 7. Isla Grace says, how big is the telescope? Now, that's a great question because it's hard to tell from this picture, isn't it, Isla Grace? So how about this one? This is a little bit easier. So this next picture is, oh no, that's going back in again. There's the one we want to show you. So that is a top part of Webb. I'm going to tell you all about it later on, but it gives you a sense of how big it is because you can see the people on the floor around. So this is a bit of the telescope, and this is a real photo But let me show you a not real photo. So this is an image that was put together by an artist, and you can see one of the teams that worked on Webb there below it. But it gives you a sense of the scale. Now, if you've ever played tennis, or if you ever watched tennis on the telly, then this silver kite-shaped bit here is as big as a tennis court. Now, Ed has asked an amazing question about this. Ed is 6, and Ed asks, how do you fit that big thing inside the rocket? Well, I've got an animation to show you this. So let's see if I can get this animation on for you. Here it is. Now, to fit Webb in the top bit of the rocket, it needs to be folded up. So that big gold bit folds up first. We're going to be learning what that is very soon. Then the silver, big tennis court size bit at the bottom folds up. And then it goes into the top of the rocket. It's attached to the top and the fairing goes around it. So it has to be folded up. Now, when Webb gets to space and it's released, it then has to unfold before it can do its job as a telescope. Talking of which, I've spotted a couple of questions that I want to answer. The first is actually a comment from Ada, who is 9, who says, you said it's a telescope, but it doesn't look like one I've ever seen. Very good point. Very good point, Ada. Yeah, there is a question from Isaac, who is 4 as well. Isaac says, how will the space telescope see? Now, I know someone who's going to be able to answer this. It's time to call my first guest of the show. She is the Astronomer Royal for Scotland, and she's joining me live from Edinburgh. Let's see how her connection is. Hello, Professor Catherine Haymans.
Hello, Greg. How are you doing?
I'm very good. Hello. Now, Catherine, thank you so much for joining us on a Saturday morning. You have a very exciting job. Tell us what it is, and also tell us where you're calling us from.
So I am the Queen's very own astronomer here in Scotland, and I am joining you today from our telescope dome in the Royal Observatory, Edinburgh. Check out our telescope. Oh yes, that's our Royal Observatory, and this is our telescope, Greg. Check it out. It's massive.
Now, I've got a telescope here, Catherine, that that people watching might be a little bit more familiar with. So this is kind of a more kind of an entry-level telescope. You can look through it and see the moon a lot closer or something like that. But what I want to know from you, I mean, who better to ask? How does this work?
Well, what a telescope does, Greg, is it collects light. And you can't see it, Greg, but inside your telescope and inside this one here is a curved mirror. Now, that mirror is going to catch the light, if you're looking at the moon, catch the light from the moon and bend that light into your eyepiece so you can see a lot more through a telescope than you can just with your normal eyes. But, Greg, if you want to look past the moon, past the planets in our solar system, past the stars in our Milky Way galaxy and out into the big wide universe, you're going to need a bigger telescope than the one you've got there and a bigger telescope than the one I've got here. Now, Greg, I want you to imagine that this little umbrella here is like the mirror inside your teeny tiny telescope. And
okay, gotcha. Well, that's
this
a bigger one.
Is my big one. Now,
okay, so let me just get this right. So the little umbrella is like the small mirror inside this telescope.
Yes.
The big umbrella is like the big mirror in the big telescope behind you. Got it.
Exactly. Now, Greg, if you and I went out on a rainy day and we decided we wanted to collect rain, we're going to put them upside down like this, collect rain, which one is going to collect the most rain?
Well, I think the bigger umbrella in your hand is going to collect a lot more rain.
It's a very easy question. Yeah, we want as big a collecting mirror as possible. Now, light from the universe is raining down on Earth all the time. And so if I want to catch as much light from the universe as possible, I'm going to need as big a mirror or as big a telescope as I can possibly get.
I've got you. Okay, now this little telescope has a little mirror, so it can only collect a little bit of the starlight or the moon's light. You've got a big mirror, big telescope, you can collect a lot more. But going back to Ada's point though, Catherine, Ada said that the James Webb Space Telescope doesn't look like this and doesn't look like your telescope, does it?
That's right, but that's because you're just looking at the outside of these telescopes. What's happening inside is just like the James Webb. You've got a big mirror that's collecting the light and it's bending the light into the camera that's at the end. So there's a camera at the end, and that camera takes the pictures and sends them down to Earth so we can see what Webb's seeing.
Got you. So the big gold thing on Webb, let's see that picture of Webb again. The big gold thing on there is the mirror. its job is to collect the starlight. And it's on the outside. I've got a little bit more about that mirror coming up very soon as well, Catherine. But before you go, I've had the same question in from quite a few people watching, from Evie, age 9, from Rob, from Theron, from Lily. They all ask, why is Webb going to space? Because we've got big telescopes on Earth, no?
Yeah, that's a great question. I'm really lucky, Greg, because I've got to use some of the biggest telescopes on Earth. I've used telescopes in the Atacama Desert in Chile. I've used telescopes. Oh yes, those are our telescopes. I've used telescopes in the on Mauna Kea in Hawaii as well. And what's amazing about these locations is they are far away from cities, far away from those street lights that make it really hard for us to see the stars. And they're also high on mountaintops above the clouds. So even if the weather's really bad, it doesn't matter. But we are still plagued by the atmosphere. So the atmosphere is only 60 miles thick, which isn't really very far, but that atmosphere, it blocks out some of the light that the universe is trying to share with us, and it also makes the light that we can see kind of a bit fuzzy. So, Greg, if you want the ultimate telescope, you have to send it to the ultimate location, which is outer space.
Gotcha. Catherine, thank you so much for coming and joining us on the hill in Scotland at the beautiful Royal Observatory. So great to chat to you. I really appreciate it. Thank you so much.
Bye, everyone.
Bye. Well, that was amazing, wasn't it? Chatting to the actual Astronomer Royal for Scotland and putting your questions to her. That was very cool. So now we know how a telescope works, and we know why we are sending one to space. And it actually turns out that some of you watching have already heard of the James Webb Space Telescope before, and you've been doing some Webb-inspired arts and crafts. So to show us some of your creations, I want to welcome into the studio here that we've set up from the UK Space Agency, it's Jeremy Curtis. Come on down, Jeremy. Thank you so much for coming. Oh, look, they've all applauded. How great's that? So, Jeremy, you've been having a look at the pictures that some of these lot have been making. Show us some.
There are some fantastic things out there. Let's start with something from, this is one of the pupils, year 5 pupil from Gurnard Primary School in the Isle of Wight. They've been doing some of the deep space diaries activities. They're great fun in school.
That's like a connect the dots to make a web picture.
That's
Love
right.
that.
We'll talk about that a bit more later. This just shows how everybody across the world's getting excited about it. This is Ahmed and Asil from Cairo in Egypt. And look at this model of Webb that they've built here. I think they're budding space engineers. They built that with their dad, Hamada.
That is so cool.
Isn't it brilliant?
So I'm loving the room. Like the decorations all around the room is amazing. What else you got?
We've got a couple of food examples here. I think these are brilliant.
All right.
So first of all, these are Nina's Webb-inspired biscuits. Look at those mirrors. Aren't they fantastic?
They're amazing.
It's
Look
so
at them.
exciting. And then Sadie felt very excited about Halloween. So look at her pumpkin. Isn't this brilliant? Again, the hexagons of the mirrors, I think that's inspired. And the whole thing, you can see the telescope there.
It's taken quite a while to make all those mirrors, hey?
Absolutely fantastic.
So good.
And then finally, someone else who's been doing some engineering as well. This is
Minecraft.
Minecraft. This is made by Kushin from Bangladesh. And again, I think we've got another budding engineer coming along here.
That is so good.
It's
so
brilliant.
good.
And then finally, from the Maldives, we've got Marshall, who's done this beautiful bit of artwork from the NASA-inspired Unfold Universe campaign. I think we've got a video as well.
Oh, let's have a look at video.
Hey everybody, I'm Marshall, and this is the space. This is me. I drew it with me and painted it. Then this James Webb Telescope over here, and this is the nebula of it, and these white dots are actually stars. Bye.
Bye. Thank you so much. They
Brilliant?
were so good. If you are watching and you'd like to get creative and make something web related, then have a look at the Webb UK website. It's here. It's JWST. Hang on. It's here. Hang on. There it is, jwst.org.uk. And the Webb team would love to see what you have made as well. So if you do want to show them off, then tag them on Twitter, tag Webb Telescope UK. That's up there as well. All right, thank you so much, Jeremy.
Thank you.
More from you later, yeah?
See you later.
Thank you. See ya. So good. I love seeing what you lot have been created. I did spot a comment during that from Simrat, who said that they've heard of another space telescope before called Hubble. And I actually have a picture of Hubble. There's Hubble. Now, Hubble was launched just over 30 years ago when I was a kid. It sits up there in low Earth orbit, a bit more than 300 miles or 500 kilometers above us. Now, the Hubble Space Telescope has captured some amazing images of space. In fact, most of the pictures that you will have seen of space will likely have been captured by Hubble, like this. Look at that. This is an image of stars forming in dusty nurseries. And this one, that is what we call a butterfly nebula, and those wings are made by stars puffing out stardust at the end of their lives. But let me show you one more. This one is perhaps the most incredible image that Hubble has taken. It's a photo of a tiny patch of the night sky, like a really small bit of the night sky. If you think of how much the night sky, the moon takes up, then it would take 10 of these squares to cover the moon. So Hubble was pointed at what looked like a boring dark bit of the sky, tiny bit, and from here we thought, oh, there are no stars or galaxies up there. We couldn't see them from Earth. But they opened the shutter of the camera for a really long time, almost 1 million seconds, that's 11.5 days, and this is what they saw. Turns out that tiny bit of the sky isn't blank at all. And each of those dots that you can see are a star. It's not a star. What am I talking about? It's not a star, it's a galaxy. It's a galaxy made up of billions of stars like our sun. Let's have one last look at it. Remember, this is just for a tiny bit of the sky, right? 1/10 of the area covered by the moon. So next time you're outside at night, look up and imagine what the whole world would look like if you could see it like Hubble does. So here then is a great question from Jim Bell. Jim's question is, if we've got the Hubble Space Telescope up there, why are we launching Webb? It's a very, very good question, Jim. Well, Catherine told us that how powerful a telescope is depends on how big its mirror is. So let's take a look at the sizes of Hubble and Webb's mirrors. So let's have a look at this. We're going to use a person to scale. This is Sylvia, 1.75 meters. Here's Hubble's mirror, 2.4 meters, a bit taller than Sylvia. There's Webb's mirror, 6.5 meters cross. That's 3 times as tall as me. And remember those umbrellas? Yeah, the bigger the mirror, the more light can be captured, which means Webb is going to capture even more light and be able to see even fainter, even further away stars and galaxies than Hubble. And talking of mirrors, Vicky here from the team at RAL has brought us something special. Should we go over and see her? Yes, all right then, here we go. Hello, Vicky. Hello, hello. Look at this.
Yeah, isn't it amazing?
So this looks like one of those mirrors. Is this a scale model?
This is a scale model. So this is the actual size of the mirrors that are on the James Webb Space Telescope.
Right, and there isn't just one, is there? If we bring up a picture, the one that I showed you earlier, that picture of all of the gold shapes locked together with the people underneath, that is how big the actual mirror is. And if you're watching, I want you to count how many mirrors you can see, right? Let's have the picture again. Bring the picture up, there you go. Okay, count them. What have we got? 1, 2, 3, 4, 5, 6, 7, 8. I lose count halfway through. Vicky, how many mirror sections are there?
There are 18 mirror sections in total. There is a gap in the middle, that black thing that you can see there, that's actually a hole where the starlight goes through to the instruments behind.
So the gap in the middle is so the starlight can go into the instruments.
Yes.
I love that. Okay, let's see if I've got any questions coming in. I have, hang on, I've got one from, which one shall I use? Actually, let me tell you first, this shape, I'm sure you can work out what the shape is. It's got 6 sides. It is a hexagon, and those hexagons fit together really well, don't they? We say they tessellate.
Fab word.
That's a fab word. All right, so I'm going to do this question from Isla, who is 6, who says, what is Webb's mirror made from?
Webb's mirror is made from a substance called beryllium.
Beryllium.
Which is a fantastic substance for space because it's very light.
Okay.
And it doesn't shrink in the extreme coldness of space.
Oh, of course, because it needs to be able to last its time in space. Okay, so it's beryllium, but it looks gold.
That's because it's been coated with a thin layer of gold to reflect the starlight.
I mean, that's a lot of gold on 18 mirror sections.
You'd think so, wouldn't you? But it's actually a very, very thin coating. So
Okay.
it's not as much as you might think.
How mega. I feel so special that you've brought us a replica of one of Webb's mirrors. Thank you so much. That is super, super cool. And I'm going to let you go and put that somewhere safe, but I'll be back later. You've got some experiments for this lot to try.
I do, yeah.
Thank you so much, Vicky. Awesome. Round of applause for Vicky, everybody. So that starlight that Webb is collecting, it's actually a special type of starlight for a special scientific instrument that is on board Webb. To find out what that is, it is time for a video from another special guest who is going to take us inside one of the clean rooms here at RAL Space and introduce us to one of the scientific instruments on board the James Webb Space Telescope. She's often finding out how things work and how they're made on CBeebies. She loves a special camera, and she's my co-host on our fun family science show on YouTube, which is called Let's Go Live. It's the one, it's the only, it's Maddie Moate.
Hi everyone, I'm Maddie and I'm at RAL Space, the UK's national space laboratory, where I've been given special permission to go inside some of their high-tech areas where they have assembled one of the amazing scientific instruments that is on board the world's largest, most powerful telescope to ever go into space, the James Webb Space Telescope. Let's go. Before we go into this area where we can see and talk about the scientific instrument, we have to go through a clean room and get cleaned up. Come along and I'll show you what that means. Hello, Sean.
Hi, Maddie.
So this is the clean room?
That's right.
What does that mean?
This is where we get changed and dressed so that we can work on space hardware.
And that's because the dirtiest thing that could go in there is basically a human.
Yes, that's
so
right.
I've got to get completely covered up.
Okay, so first we need to put these little blue shoe covers on.
All right, shoe covers on to cover up my trainers because they could have some muck on them. One. So I've got my shoe covers on and I've now stepped over to the clean side of the room.
That's right.
All right, what's next?
Okay, so next we need to put a hairnet and we need to change your mask.
So now feel a little bit like a duck. There we go.
So we put another layer on your head. This is a hood.
This is the most amount of protective clothing I've ever worn and we're not even finished yet.
So the goal here is to not get the suit dirty.
Right.
So it's a test of your balance. Then we have another pair of shoes that go over the top.
So these are overshoes?
These are overshoes.
I don't know what else we could cover other than my eyes.
And then the last thing we do is we put a pair of gloves on.
I feel like I'm about to go into surgery.
And there you go. You're
I'm done.
You're ready.
I'm officially clean and allowed to go into the next room.
That's right.
Okay, Mandy and Greg, they're all set too. In fact, come over here. This way. Mandy, Greg, we're all clean, which means we can go on in. This way. Hello, Catherine. Hi. It is very impressive to be all dressed up and inside a clean room for the first time. What happened inside rooms like this?
This is where we build instruments that go into space and prepare them for the testing we have to do before launch.
And why is it so important that we look like this?
Because any dust that ends up on the instrument, anything like that, we can't clean off when it gets into space. So it's really important that we keep it as clean as we can now so that there's no chance of dust particles landing on a lens and causing issues once it's in space and once we can't do anything about it.
I understand that you and the team here, you are responsible for putting together one of the instruments that's going on board the James Webb Space Telescope. And this is it. What is it?
This is MIRI, and this is one of the 4 instruments that's going to be flying on the James Webb Space Telescope. MIRI stands for Mid-Infrared Instrument, which means that it's looking for tiny bits of heat really far away to try and work out how the universe started.
Just a small job.
Yeah, quite difficult.
Just trying to work out how the universe started. That word, infrared, it reminds me. I want to show you something. Bear with me, Catherine. Infrared, let's talk about that. Infrared is what MIRI uses to help the James Webb Space Telescope look deep into space. It will allow us to see through dusty space clouds where new stars are born, and we'll even be able to see planets like Neptune and Uranus in brand new ways. But how does it work? Well, let me explain. We see the world in visible light. That's light that comes from the sun or from a lamp that we switch on at the wall. However, MIRI uses infrared light. And thankfully, so does this camera. It essentially shows us how hot or cold things are. Look, if I point this in front of me, we can see Mandy behind the camera give us a wave. There's Greg. Hi. And also, we have the RAL Space team. Hello. I've got an idea for an experiment. Greg, will you come and join me?
Sure.
Here we go. Let's just focus on you. Nice. Let's take a close look at Greg's face. So, What colour is Greg's face? It is red. That means Greg's face is pretty warm, but your nose is yellow. Touch your nose. Would you say your nose is cooler?
It's cold.
Yeah, in fact, your finger is blue, so your finger must be much cooler than the rest of your nose.
To be fair.
Yeah? And if we look around Greg's head, we can see it's blue and purple, which means it's much cooler. Now, I'm going to point this at Greg's feet, because Greg has conveniently taken his shoes off. So right now, we can see that Greg's feet are really hot because they look red. But now, Greg, take a step to your right, and look. With my eyes using visible light, I can't see those footprints. However, the heat has transferred, that thermal energy has transferred from Greg's feet to the floor, and the infrared light can see it. So that's a little bit like how MIRI is working. Let's try one more thing. Greg, you have a bin bag. We're going to pretend that this bin bag is a dusty cloud of dust and gas up in space. We call them nebula. And Greg's hand, which is inside the nebula, is a star. With visible light, we can't see the star, can we? However, if we use infrared light, which is what MIRI uses, suddenly we can see that star. And look, if Greg moves his fingers, that star is even twinkling. So this is what MIRI is going to do. It's going to allow us to look through nebula to see stars being born. It's going to allow us to see things that we have never seen before, which is very exciting.
Thumbs up.
Thanks, Greg.
Welcome.
Right, I've got to go join Catherine.
Have fun.
Bye. Sorry about that, Catherine. So, MIRI, we can kind of think of it a bit like a special camera. Are you able to point any bits out to me?
Yes, so first off, the light comes in through the bottom of the camera here. Then there's a mirror, and the light bounces off the mirror, and like a periscope, it then goes up into the instrument. So the light gets split into these two detectors here, and all the information goes through all of these wires back to the spacecraft, where it goes back down to Earth, and the scientists can learn about what's happening in deep space.
This isn't the actual MIRI that's on board the James Webb Space Telescope.
No, this is what we call an engineering model. All of the different parts of it are very similar to the actual instrument that's currently on the James Webb Space Telescope, but it allows us to do some testing of the instrument that isn't the real instrument.
The actual MIRI was put together inside this very room, though. But for it to go into space, it doesn't look like this. This one is a bit like a scientific instrument that's not wearing any clothes. If this was to go into space, a few things would need to happen to it.
Yeah, so before we send it into space, we need to fit something called multi-layer insulation. And that's like a really fancy, shiny blanket that goes on the outside of the instrument and protects it from the really hot and really cold temperatures that it might see in space.
And that's something that you do.
Yes, so my group, we build multi-layer insulation and then fit it to instruments to make sure that they don't get too hot.
How does it feel to be part of something so important?
Oh, it's very exciting. Some of the scientists and engineers have been working on it for 20 years now, so it'll be amazing for them to be able to get results down from the instrument finally.
Amazing. Well, thank you so much. In my next video, I'm going to be talking more about the testing stage. But for now, I just want to say, Catherine, thank you for having me and showing us around a clean room.
Oh, thank you.
Well, thank you both. Thank you, Maddie. Thank you, Catherine. That was great, wasn't it? Lots of you loving that on the live chat. I fixed my live chat. It stopped working, but it's all good. Right, hello, Johnny and Ada from Highworth, and Callum and Finley from Scotland, and Zach and Izzy from Weston-super-Mare, and Beth and Sam and Tommy from Radley, and Ali and Amy and Tim from Nottinghamshire, and Dexter's age 13 and really wants to work in space one day. Awesome, me too. Loads of great questions about the mirror. Loads of people loving that video. Keep them coming. Keep them coming. Thank you all so much. So, as Maddie just mentioned, there is another video coming up later in the show where she discovers how the engineers here at RAL Space test spacecraft and scientific equipment to make sure they can cope with the shake, rattle and roll of a rocket launch. That video also going into this amazing thing behind me. Let's see this again on the wide, Owen, because where we are right now doing this live is cool. And let's just remind them that it's quite noisy. Should we flick the filter off? It's quite noisy here, you lot. This is what's happening right now. But it's doing cool science. So let's put the filter back on. Okay, lovely. I'm not going to tell you what that is just yet. I'm just going to tell you that it's awesome. So we just learned about a special type of light called infrared light, but that is not the only special type of light. And to find out about some of the others, I thought we could do a quiz. Now, we always do a quiz dance on our family science show, Let's Go Live. So hit the quiz music, Owen. Let's see you all dancing. Wide angle. Come on, crew. Everyone, guests. Let's see you all dancing. There we go. You lot at home. Brilliant. Okay, that's enough of that. Good job. Good job. Good job. So this is a quiz about light. But there are different types of light. Now, the light that you are seeing me with right now is called visible light. We've just heard about another type of light called infrared light. So let's add both of them onto there. Now, light travels in waves, and the waves of infrared light are longer than the waves of visible light. Here are some other types of light. Let's add them all. And you can see they're organized by how big their light waves are. So radio has really long wavelengths, down to gamma rays with really short wavelengths. So here is the quiz. I'm going to show you an object, and you've got to work out what type of light it uses or relates to. All right? Okay. If you know what it is and you're watching live, put it in the live chat. If you're watching back, yell it out nice and loud. Okay, first object is this. It is a lamp. What type of light does this lamp give out? We can see the light. It is visible light. Pop that on visible light. Okay, good, all right. How about this image? Here's another one. This was created using a type of light. It's a type of light that can be used to see inside our bodies. Where do we put it? Where do we put it? X-rays. Yes, so this was taken using X-rays, allows us to see our skeleton inside. Okay, let's try another one. What is this? It goes bing. It actually uses a type of light to cook your food. It makes the water molecules in your food shake lots, and that heats them up. It is a microwave, and it uses microwaves to cook your food. So that goes on microwaves. Okay, let's have another one. If you don't know what this is, you might want to ask a grown-up what this is, because this used to be how you'd listen to music before the internet could stream it, all right? This is a radio, and that music was sent across the world using radio waves. So that needs to go up at radio waves. Okay, we're getting there. Here's one more. What's this? That's some sun cream. Okay, and this protects your skin from a type of light, a type of radiation. What type? What do you reckon? It's ultraviolet. So we use sun cream, we put it on our skin to protect our skin from ultraviolet radiation. So here's another one then. Here's another type of radiation. What clue shall I give you? This one's waves are very close together. They've got a lot of energy. This type of radiation can be made and used in a variety of different ways, including to treat us when we're sick. These are gamma rays. They are gamma rays. How you doing? You doing good? Okay, you've got one left. You've seen this one before. Let's bring up this picture. This is the picture that Maddie took of my face using what type of light? Do you remember what type of light it was? It's the only one that there's a gap. Infrared light. Put that down there. And that is the type of light that Webb is going to use to look at the universe and make the invisible visible. So this is the complete spectrum of light, or as we sometimes call it, the spectrum of electromagnetic radiation. How did you do? How did you do? Let's have a look what we've got here. Well done to Callan, guessed X-rays. Teddy, age 10, guessed X-rays. Stanley, age 11, guessed microwaves. Madison guessed ultraviolet. Well done indeed. Hello also to Leo and Toby in Dorset and Jack and Chloe in Chelmsford and William and Charlotte in South Cave. It's great to have so many of you watching us, and well done on the quiz. Well done, everyone. How are you enjoying the live mission briefing so far? Do let me know any questions that you have about Webb in the live chat so I can put some of them to my expert guests. I've seen quite a few coming in asking how Webb is going to get to space. Well, the short answer is inside a rocket. Oh yeah. We're going to be joined by someone from the European Space Agency very soon to tell us all about the rocket launch. Before that though, let's learn a little bit more about Webb, shall we? We now know that Webb, hang on. Hey, we now know that Webb has got this big special mirror with 18 sections, beryllium and gold coated, and that's going to there to collect lots of starlight. That's what makes it the largest, most powerful telescope ever launched into space. We also know that there are 4 amazing science instruments on board, 4 special cameras, one of which is MIRI. That one's going to be looking out deep into dust clouds where new stars are being born. But what we haven't yet learnt about is this amazing silver kite-shaped skirt. What do you lot watching think that's for? If you're watching live, let me know what you think that's for in the live chat. To find out, I want to welcome someone here who knows a lot about Webb. He is the chief engineer here at RAL Space. It's Paul Ecclestone. Hello, Paul. Hello, hello. Oh, I love this. Thanks so much for joining me for the show. So tell me more about being a chief engineer, and also tell me a little bit more about the cool stuff that happens here at RAL Space.
So as chief engineer, I get to come and play with all the different projects and things that we've got going on here, where we're building cameras and instruments that are going to go up in space, either to look down at the Earth and look at climate change and things, or to look out into the distant universe, like Webb's going to.
Mega cool. I mean, what a place to work.
Oh,
I mean,
great.
come on, that is so cool. And I just asked this lot what they think the shiny skirt might be.
Yeah.
So I'm going to bring up my live chat and see if we can get some of those suggestions as they're coming in. What is it?
It's actually a Sunshield.
A sun shield. Okay. Tell me more about it then.
So it's there to keep the bits of the telescope that need to be cold, really cold, and the bits that need to be warm, warm, by stopping the light from the sun and the Earth getting to the bits of the spacecraft we don't want it to see.
But hang on, you've therefore said that space can be not just cold, like we heard earlier from Vicky when we're looking at a mirror, but also hot. How can space be hot as well as cold?
So it depends what you're looking at. If you're looking out into deep space, it's really cold, really, really cold. But if you're looking at the sun or warm things like the Earth, then actually it's quite warm. And particularly when you're facing the sun, stuff can get really hot.
Okay, so hang on a minute. The sun shield is therefore a little bit like, hang on, it's like a giant umbrella.
It is.
Like a parasol that you put up at the beach.
Exactly
right?
like that.
And what you want to do is you want to make sure that the scientific equipment and any technical stuff is shaded from the sun on the other side.
It's got to always stay in the shade.
Right, right. And actually, we've got a little animation of how Webb will travel through space, because this is amazing. It travels through space on its side with a mirror kind of protected, and the scientific equipment protected in the shadow of the sun shield. It keeps the instruments, I guess, in a continual cold night.
Exactly, permanently shaded away from the sun.
And why do the instruments need to be kept cold?
So we need to keep telescope and the instruments really cold to make sure that they don't glow. Because we're looking in the infrared with Webb,
yes,
they've got to not see anything that's warm.
Yes, now we saw that with this picture that Maddie took of me before. I'm glowing, so is the worry that Webb would be in the picture?
Exactly, so this was you giving off infrared light. If we had the cameras and the telescope glowing, then it wouldn't be able to see the really faint, really distant things that it's going to be looking at, because all it would see was itself.
I see what you mean. Okay, so because it's going to be looking at such distant stars and galaxies that are not giving off much starlight, it's only going to be kind of cold, pretty faint. And you don't want to see yourself in the picture.
No, exactly. So it's got to be really, really cold that side, minus 230 degrees.
Wow, chilly. I've got a question here, Paul. It's from Jack.
Yep.
Jack says, what is Webb made out of? Does it have to be a special material to go to space? We've heard about the mirrors.
Yep.
What about the Sunshield then? What's that made of?
So the Sunshield is also made of a special material. It's something called Kapton, a plastic, special type of plastic, which can get really hot and get really cold. But it's then coated with aluminium on both sides. So it's actually a very similar material to what crisp packets are made of.
Hang on. I've eaten crisps, right?
Yeah.
And I know that those crisp packets, they rip pretty easily. So could that rip?
You've got to be very careful with it to make sure that there's no little tears, because crisp packet material, it's really hard to rip if there's no tear to start off with.
Oh, you're right, it is hard at the start, and then it's easy.
And then it's dead easy. So they've made sure that there's absolutely no way there can be any little nicks or holes or anything in it to start those tears. And so that when it's folded up and compressed inside the rocket, none of those tears can start and get out onto the Sunshield.
Does it make you nervous about the launch?
Always a little bit nervous when these things are going up on a rocket, but Webb's been tested and tested so many times to make sure everything's going to go right, because we absolutely want to guarantee that there's nothing that can go wrong. So I'm pretty confident that there won't be any big problems.
That is fascinating to hear what it's made of. Thank you so much for coming in and telling us all about the Sunshield. I'll let you get back to your important work. Big round of applause for Paul Lee. Thank you, Paul. Let's have a look at what you lot were suggesting. Well done to Aurora, who guessed a protective shield. I think my favourite on here, oh, this is great. My favourite is a trampoline for stars. That's a great guess. I love that. All right, so let's crack on. So Webb's Sunshield is super important to keep the sensitive scientific equipment cool. But there is another way that you can keep the equipment cool. Now, in Maddie's video earlier, the MIRI video, remember when she met MIRI with Catherine, she told us that what they do is they wrap MIRI up to keep it cool, right? This is it unwrapped. Let's bring up this picture. Unwrapped on the left-hand side, wrapped up on the right-hand side. Catherine mentioned that it's wrapped in something called multi-layer insulation, or MLI. I've actually got some of that here, which is pretty mega. Here is some of the MLI that is used to wrap up stuff that's going into space. And in here is actually some of the special stuff that they used on MIRI. Very, very cool. So it can help keep equipment cool when it's hot outside. It can help keep the equipment warm when it's cold outside. And Vicky has an experiment that you can try related to this. Hello again, Vicky.
Hi, Greg.
Hello, hello. So you've got an experiment for us.
I have, indeed.
Let's see it. Let's see it. What have you got for us?
So we're going to do a simple experiment. It's something you can do very easily at home with household bits and bobs. And we're going to make our own spacecraft insulation.
Oh, so we're going to make like a space blanket.
We are.
For a spacecraft.
We are.
Lovely. What do people at home need for this?
So first of all, you need a spacecraft.
Wow. Oh, hang on. Top quality spacecraft we're looking at there, a glass. Okay, gotcha.
Okay, and then anything you can find really that might give it some insulation. So I've got some tin foil. I've got some netting from your Christmas oranges.
Come in, Adrian. Let's have a look at this. So, okay, so you've just got a bunch of different types of material here. Bubble wrap, net. Where do you say you get the netting from?
You know, when you get your oranges from the supermarket, or you get in them in a net. You can use that.
Foil. Okay, gotcha. All right.
And then you layer it up to try and make some nice air gaps in between your layers of foil.
Now, this is something I didn't realise, because I thought, oh, you'd layer up these different layers of insulation, which would keep everything inside cold or warm. But this is a bit of the actual multi-layer insulation. And you can see, as you said, it's actually layered up. Adrian, come in, let's see this. So you can actually see it's layered, right? And then there's some of that netting, and then there's another layer and some more of that netting. And why is that important?
Because we want to create a gap between the layers so that they don't touch.
Right.
Because we're trying to stop conduction through.
Stop the heat flowing through the material.
Yeah, we don't want the layers to touch, so the air will protect it, so the net will stop it from touching.
Let's do it. Let's build ourselves a spacecraft.
So you can layer up your stuff.
Okay.
Very briefly, like this, and then wrap it up. And then get some sellotape, make sure that you make a nice bottom for it.
Yeah.
And also you can even make a lid to make sure that it stays nice and insulated inside.
Right.
And here's one I made earlier.
Here's one I made earlier. Great, here it is. Okay.
Here it is. Yeah, so this is my spacecraft. So we've had 2 glasses with ice cubes in here. This one has been, well, they've both been sitting here for about an hour now.
Right.
This one, as you can see, has got a little bit runny, as you would expect.
Oh, well, that's melted to be expected. It's quite warm in here.
Yeah. And should we take a look and see?
Yes, it's the moment of truth.
So
no pressure. It looks good.
Oh.
Yeah, I mean a bit of melting, but come on.
But
I mean, look at those ice cubes there.
You can still put them in your drink.
Compared to, well, now not that I've touched them, but you know, those ice cubes there, much better. So that's because you insulated the spacecraft with the glass.
Yes, I take space.
And stop the heat getting in, just like the multi-layered insulation protects spacecrafts and equipment in space. I love that so much. Thank you so much, Vicky. And if you lot watching want to have a go, please have a go and let us see what you do. Maybe you could have a little challenge, you know, within whoever's at home or at school or whatever, to see who can make it last the longest, right? The ice before it melts. Vicky, thank you so much.
You're welcome.
I believe you've got one more little experiment for us later. Brilliant, brilliant, brilliant. Thank you. I've now got wet hands. I didn't think about that, did I? Right. So many questions coming in from you lot watching live. So thank you so much. Keep them coming. I'm seeing them shoot in on my screen. If you missed the start of the mission briefing, where have you been? You've missed a big telescope in Scotland. You've missed a light-related quiz. You've missed when Maddie met MIRI. which sounds a little bit like a film, doesn't it? I should perhaps repeat again that I am coming to you live from Royal Space, the UK's national space laboratory. And right now, this is what the James Webb Space Telescope looks like. It's actually mounted. Rocket is underneath that kind of false ground there. And the bits you can see on the side are what we call the fairing that are going to go round the top of Webb to protect it. And it's then going to be taken out onto the launch pad of Europe's spaceport at the Guyana Space Centre in Kourou in French Guiana on the northeast coast of South America. There will be a countdown and then it will blast off into space. And in fact, I'm about to be joined by someone who's going to talk us through what will happen during that launch and what will happen to Webb in the 6 months or so after the launch as it makes its way to its destination and it unfolds and it gets ready to do science. First though, Webb has already been on quite the adventure to get to French Guiana. Let's take a look. Cue video. Cue video. We're live. Webb's journey started in America, in California. First, it needed to be packed up into a protective container for safe transport, and then it was driven with a police escort down the highway to Seal Beach, where this ship was waiting for it. And after 16 days at sea, covering almost 6,000 miles, that's over 9,000 kilometres, it arrived in Kourou in French Guiana, South America. Webb was then unloaded and it was driven to the Guyana Space Centre. Once inside the clean room, it was unpacked and raised up, ready for launch prep. It was carefully attached to the transport ring, then it was taken for fueling. Now, this is the most dangerous operation while it's on Earth, so people wear these special suits. After fueling, it was taken to the vehicle assembly building and lifted up, and placed on top of the Ariane 5 rocket that will launch it into space. Oh, so that is how it got there. What comes next? The launch. To explain what is going to happen, I'd like to welcome onto today's live mission briefing Dr. Tim Rawle from the European Space Agency. Hello, Tim.
Hi, Greg. Nice to be here.
Oh, thanks so much for coming. You've come a long way as well, right? Thank you so much for coming. So it's time to talk about rockets. So first of all, tell us a little bit about the European Space Agency and what ESA, is what we call the shortened version of it, what ESA's role is in this really exciting Webb mission.
Right, Greg. So more than 20 years ago, the European Space Agency joined NASA and the Canadian Space Agency in a very ambitious partnership to try and launch the largest telescope that's ever been in space. So ESA's contribution includes 2 of the 4 science instruments. We heard about MIRI and also NearSpec, which is actually the instrument I work on.
Cool.
But the main contribution of Europe to the mission is the Ariane 5 rocket, which will launch from the European spaceport in French Guiana.
Gotcha. Now, we are looking at a picture here of, I think this was yesterday or the day before. This is like the most recent picture we've got. Webb's folded up. It's on top of the rocket. The fairing's about to go on. What happens next?
So next, about a day before launch, we roll the whole rocket out from the assembly building to the launch pad.
To the launch pad. Now, this is a picture of a rocket being taken out a few years ago, but what an incredible sight that is. And I want to know, oh, actually, it's not just me who wants to know. Let's see if I've got some questions. Flo, who's 6, says, what happens when the countdown counts down to 0? Okay, so for you, Flo, and everyone else who wants to see this, I've seen so many messages for this. There's an amazing animation that we're going to play. And Tim, you're going to talk us live through what happens when the countdown counts down to 0.
Definitely, it's very...
Challenge accepted? Okay, let's roll this animation.
Okay, so here we have the Ariane rocket on its launch pad about 10 seconds before launch. Now, Ariane launches in French, so listen out for 3, 2, 1, top. And at 0, this main engine then ignites. And there it is, it's a beautiful sight. But we don't actually lift off for another 7 seconds until that engine reaches full power, and the 2 boosters strapped on the side also light up.
Now, Connor, who's age 7, has just asked, will there be people on it?
So Webb is actually a completely robotic telescope. So we send commands from mission control, but no humans have to go up there.
Gotcha, okay. And so the boosters at the side, as you say, that's what's giving that initial thrust. And we should be able to see that in the animation now. What happens when all that fuel's run out?
So those 2 boosters actually only last about 2 minutes. and they take the rocket to more than 7 kilometers per second, and they run out of fuel, and yeah, they're jettisoned, as we can see there.
Henry says, where is it going to land, or will it just float in space? Catherine says, will it orbit the Earth?
It will actually just float around in space, in fact. So it's a very good question from Catherine, because you may be aware that Hubble orbits the Earth at about 570 kilometers. Webb will be much, much further at 1.5 million kilometers, which is about 4 times as far as the moon.
Gosh. So we saw the fairing came off to reveal Webb, and then another bit came off. Tell us what we just saw.
So the main stage runs out of fuel as well after about 9 minutes, and that separates, as you saw. Now we're on here, the second stage, which lasts for about 25 minutes, and it gets Webb to the speed it needs to get to take it out beyond the moon. Gotcha. And here we just saw that also run out, and then that separates, sending Webb on its way.
Oh, now actually what's amazing about this is getting it into space, doing all of that, the launch itself, that's only part of the story, right? Because what happens now is phenomenal, and it just blows my mind. So I'm going to do one more animation.
Sure.
Tell us what we're seeing, because this is incredible.
Of course. So for the next month, Webb is traveling to its destination, and it has to now unfold. So first we saw the solar panel extend to give a spacecraft power, and now that big Sunshield that Paul was talking about also extends out to its full size, tennis court size. Then the secondary mirror has to deploy on its tripod, and then you just saw finally those 2 wings of the main mirror fold into front screen.
So all of that is happening while it's going off to, you said 1.5 million kilometers away from the Earth.
Exactly, yes.
So all of that is happening, and then how long will it be until it can start doing science?
So once it's there, after about a month, we still have to wait for the instruments to cool down completely, which takes about another month. After that, we can start turning instruments on and setting them up, which takes another 4 months. So it's going to be 6 months after launch when we really start getting those beautiful data that the astronomers like to see.
Well, I'm going to get to chat to an instrument scientist who's going to be using Webb very soon later in the show. Tim, thank you so much for coming and explaining. You've got one of the coolest jobs in the world. Thank you, Tim. Huge round of applause for Tim.
My pleasure.
Brilliant. Cheers, Tim. Oh, I have had so many great questions in from you lot as well. I've had a super question in from Seth via Facebook. And Seth says, I would like to be an astronomer one day. Seth wanted a Hubble Space Telescope for his 5th birthday. Good choice, Seth. And Seth says, how will the telescope be kept safe on its journey? Now, that is such a good question, Seth, and I'm going to answer it in 2 parts. So first, I want to speak to someone who helped build Webb and whose job it was to make sure that it was built to survive the launch and its journey up into space. And then I want to play you a second brilliant video from our roving reporter, Maddie Moate, who came here to RAL Space a few weeks ago, who got to see how the spacecraft are tested before launch. But let's start with that call. I'm going to bring in a mechanical engineer who worked on Webb, Pial Samara Ratna. Are you there, Pial?
Hello, everyone.
Hang on, let's see that jumper first. That looks like a cracking
jump. Thank you. Yeah, well, I'm very lucky that my role on Webb is over, so I can concentrate on being more like this guy.
So tell me what your role is on Webb, or was on Webb, and why it's over.
Yeah, so I work for the University of Leicester. I am a mechanical engineer, and we are the lead mechanical engineers for the MIRI instrument. So we make sure that it all goes together correctly, it all gets correctly put onto spacecraft, and to make sure that it's both strong enough to survive launch, so as it goes in the rocket, it doesn't fall apart, and also that it survives in that really harsh environment of space. But it's also got to be super, super light as well, or the rocket's just not going to be powerful enough, or the spacecraft's not going to be powerful enough to take it to do what it needs to do.
Gotcha. So it needs to be strong, but it also needs to be light. And that's obviously going to play into the materials we've already heard about, the light material for the mirror, the light material for the Sunshield. But explain what you said earlier, that you're no longer working on it, and also answer a question from Harrison, which is, how long did it take to build Webb?
Yes, so Webb's taken a long time. It's taken well over 20 years to get the spacecraft here. When people thought about how can we actually be better than Hubble, they realized that they actually had to invent things that had never been invented before if we're truly going to explore the universe and do better things. So all those things had to be invented. We started building MIRI about 20 years ago and delivered it to NASA about 10 years ago. And and all of that's just I've been preparing, getting it ready for launch, and making sure it can do the best possible job.
So how many people do you reckon worked on Webb?
Oh wow, there must be thousands of people here. Like there are of course the engineers and scientists responsible for building Webb. Then there are also scientists responsible for making sure that when Webb is operational, it does the best possible job to do better than Hubble. But there are also managers, lawyers, delivery people, people who make sure we're talking about Webb, make sure the world really benefits from Webb, all around the world, making sure that this all comes together.
It's such a good point, Pio, isn't it? That like it's not just the scientists and engineers; they're incredible, they do amazing stuff, but it's the whole team. Like it's a huge team involved. I'm going to ask you how you feel about the launch, because something that you spent a lot of time on is about to launch on a rocket.
Oh yeah, it's so exciting. Like as an engineer, I've been lucky enough to be able to design things. I've tightened bolts, I've put glue down on things that are now going to leave the Earth and go into this place and hopefully stay around there for a long, long time. And that's a real privilege and really, really exciting. It's also a bit scary, to be honest, because we do a lot of things to test and to practice everything working right. But now comes the real moment where we actually find out it's all going to work to come together. So it's also a little bit scary as well.
Yeah, I'm sure it is. Look, PL, thank you so much for joining us on a Saturday morning. Really appreciate it. Thank you for all your hard work, all the team's hard work on MIRI and indeed on Webb. I'm going to have to say goodbye, but it's could chat to you for hours. Thanks, PL.
Thank you.
See you. Bye. So that is how Webb was built to be as strong and as light as possible. It's time for the second half of the answer to your question, Seth. After the telescope has been built to be as strong as possible, it then needs to be tested to not only make sure that it will survive the launch, but it also survive the journey into space and its future life in space. Our roving reporter, TV presenter and YouTuber Maddie Moate came here to RAL Space a few weeks ago to see those tests in action and to see how MIRI, which is the scientific instrument that we learnt about earlier, was tested to be ready for launch and life in space. Over to you, Maddie.
Getting something into space, whether that's a satellite, a spacecraft, or the James Webb Space Telescope, it takes a lot of oomph. You need a lot of force to overcome Earth's gravity and get us out beyond the many layers of our planet's atmosphere. It's why rockets have such big boosters. They're filled with rocket fuel, and when that fuel is ignited, that makes a lot of force out and down, which sends the rocket up, up, and up. But during launch, the thing you want to get into space, that might be the telescope or the satellite, we often call it the payload. That payload is also going to experience the wild ride. It's going to be traveling very, very fast, and things are going to get pretty shaky. Often, it's also a highly sensitive piece of scientific equipment that scientists and engineers will have spent years and years making. The last thing you want is for it to get damaged during launch. You get to space, find out it doesn't work, and then what are you going to do? It's not like you can just nip out and bring it back to fix it. So how do you prepare something like this for that wild ride into space? Well, that's what I'm here to find out here at RAL Space, the UK's national space laboratory. Anything that goes into space has to go through a series of tests, and this is the first one. Hi, Charlie.
Hi.
Right, what on earth is this?
This is our shaker.
A shaker, that sounds pretty simple, but what does it actually do?
Basically, the launch is quite violent and everything that goes up into space gets shaken a lot. So this is to make sure that by the time it gets into space, it hasn't shaken itself to bits.
So something like MIRI, that would have been tested on here?
It was indeed.
All right, what's this here?
This is just a box. We do it ahead of a test to make sure that we know what we're doing. But it gives us a good idea of how the thing will react when we do it for real.
Can we give it a go?
Yes, we have to put ear defenders on if you want to grab some.
So it gets pretty loud?
Yes, it can get very loud.
Shake, rattle and roll. There it goes. What? No. Imagine being inside a spacecraft, being rattled around that much. You need a lot of nuts and bolts to not fall apart. Come on. But whoa, Charlie.
That's the kind of force that any type of payload has got to put up with. Is that still moving? Wow. That's now shaking so fast, our eyes can't actually see it happening anymore. It looks still, but that's how quickly it's moving. And now it stopped. Whoa, that was cool. This is our next test. Tom, what is this huge machine?
This is our PyroShock simulator test.
The PyroShock simulator test. What does it do?
Basically, it's a massive air tank and a barrel with a slug that fires along it.
Hang on. That's not the kind of slug that I know. What's that?
It's a projectile, basically. So it fires along this barrel at quite a high velocity, strikes the back of this plate, and then our test light hits.
So actually, this is where a bit of scientific equipment would go. Something like MIRI would go here.
Yes, on something much bigger than this, because MIRI's a lot bigger. But yeah, exactly.
Why are you doing that? Why are you firing things at the plate?
When we're in space, rockets have to separate. And while they separate, they do it using explosive bolts. And those explosive bolts send shock waves through the structure. And we use this machine to make sure our test items can survive that.
I can't believe spacecraft are connected together with explosive bolts.
Yeah, it's crazy.
Can we use it?
Yeah, we are going to have to go out because it is very loud, though.
Do I get to press the button?
You do. Let's go.
The button's flashing. Can I press it?
Go ahead.
3, 2, 1, blast off. That was quicker than I thought it was going to be. Should we see that again in slow-mo? Here it is.
So here's the plate that the projectile struck.
What metal is this?
Aluminium. So it's not the strongest metal in the world, but it's definitely not the weakest.
Can I see it?
Yeah.
Look at this. Can you see that dent? I have to be clear though, because the equipment that would be tested here on this machine, it's not actually going to get struck by a slug in this way. But what this does, it helps us to recreate the type of shock wave that the equipment might experience on its way to space. It's very impressive to know that everything on board a spacecraft has to be able to withstand this type of shock. Whoa. Whoa. For our first test, we made sure that the payload could survive the launch into space. Test 2, we wanted to make sure that the payload could last the journey into space. And test 3, the final one we can see today, is in there. That's where we'll make sure that the payload will last a lifetime in space. But for that, I need to get changed. Welcome to the Space Test Chamber Clean Room. John, can I borrow you?
Oh yeah, sure.
Everybody, meet John.
Hi, Maddie.
Hiya. What happens in here?
Here, we test spacecraft and we recreate the conditions of space.
What do you mean by that? How are you recreating space conditions?
Okay, well, space, there's no air. So we recreate a vacuum in this chamber. And also in terms of temperature, we make it very, very hot or very, very cold.
All right, so how do you make a vacuum?
Oh, we've got lots of pumps that suck all the air out, and then it sucks all the water vapor out and creates a really low pressure.
And that's because there's no air in space?
No air and no water vapor. So we get rid of all that.
And then you mentioned temperature as well. What temperatures are you getting inside that chamber?
Here we can heat up to 120 degrees.
120 degrees Celsius. So if you imagine boiling water, water usually boils at about 100 degrees. That's 20 degrees hotter than that. But then you said cold as well. How cold can it get in there?
Here we can go down to about minus 190 degrees Celsius.
Minus 190. That is chilly.
Pretty chilly.
We often think of space as being really cold, but not often hot. How can it be both?
Yeah, so sometimes when you're facing the sun, things get really hot. And if you're in the cold, black emptiness of space, things can get very, very cold.
So really, it's a matter of whether your spacecraft, your scientific instruments are in the sun or they're in the shadow.
That's right.
So all of that is happening inside that chamber.
That's right.
Can we see inside that?
Yeah, sure. Go on, follow me.
Okay, we shall. After you. It's just huge. Whoa! No way! I feel like I'm in a movie set. What are these?
These are the shroud panels. These are what get really hot or really cold. We flow liquid nitrogen through them.
So the liquid nitrogen cools them down.
Exactly, and then there's heaters on them as well, so they can get nice and hot. We've got 46, and they can each be a different temperature, or we can go half hot, half cold, or any combination.
Was something like MIRI tested in something like this?
MIRI went through a very similar test in one of our slightly smaller chambers.
Right.
So MIRI was tested for 100 days, 84 of those at operating temperature.
100 days?
But this one, we can go for as long as 9 months.
What?
Yeah.
Okay, because this is testing how something is going to survive a lifetime in space,
That's right.
It's important that the test does last a really long time. How does it feel to be part of an ongoing test that could be 9 months long?
Well, it's really exciting, but you have to be very patient.
You can't just take a little peek in, can you? Because you'd let all the air in and then you lose your vacuum.
We've got to close the doors, and then we just got to test and wait.
Thank you so much. What an amazing test to end on. Can you imagine waiting 9 months for the results of something you were testing? I can't.
How amazing was that? And that incredible vacuum chamber is what is behind me. So we are on the outside of it, and it's doing its thing. It's very, very noisy here, I tell you. But that is the outside of where Maddie was inside. Super cool. Anyway, let's come back. Hello, hello, hello. Let's get straight to Vicky, because Vicky's got a really fun experiment that you can try related to the tests that Maddie just showed us. Vicky, hello again. Hello, hello. What have you got for us?
Okay, so this is another fun thing you can try at home using spaghetti and blue tack.
Okay.
And a tray.
Okay.
If you don't have a tray, use like a clipboard or a book or some cardboard or something, but you need to have a base for it to sit on.
So you've made your, I can see you've made your version of Webb here.
Yep, as you can see, I'm a wonderful engineer.
You are a spaghetti engineer. Look at that. That's masterful. And which bit of, I think I can guess, which bit of Maddie's video are we recreating here?
We are going to recreate the shaker table. So we're going to test this for launch.
We're going to test this for launch.
Yeah.
Okay,
Are
all
you
right.
prepared to help me with this?
So we don't have a shaker table, so that's why we're using a tray.
Normally,
Okay.
if you came here to do a workshop with us, we've got a miniature shaker table we can put things on to test it. But unfortunately, not everybody has one of those at home.
No, for sure.
So,
Yeah, I don't.
So we're gonna test it together by shaking this tray.
Challenge accepted. All right. So let's see if our Webb spaghetti space telescope will survive launch. Yeah.
Go.
Well, you're not holding back. Oh no! Oh, Webb. Okay. I think that might be. I mean, look, when things like this happen, that's always very useful. Okay, as engineers, as scientists, we can redesign. We can go again. So good luck redesigning.
I'll have another go at that one.
I love that. But look, if you don't want to try that at home, you can try it with spaghetti and blue tack. You could try it with marshmallows.
Yep.
And little like twigs or whatever you can find.
Play-Doh, pencils.
For sure.
Whatever.
That's so good. And Vicky, thanks so much for coming along and doing this demo and the space blanket and also bringing us the mirror. I really appreciate it.
You're very welcome.
Thank you so much. Well, I want to see you lot make some of your own shaker tables at home. There is one big question left to tackle for this live mission briefing, and it was asked by Ishael, who is 9. And Ishael asked, what is the telescope going to look at first? And this is such a good question because the universe is huge. So where do we look first? Well, let me call one of the scientists who will be using Webb once it is up there in space. Let me call Dr. Pamela Clarkson. Hello, Pamela. Hello. Oh, I can't hear you at the moment, Pamela. Are you muted? I've got you. I've got you. No, you're good.
All right.
It's my end. Hello. How are you today?
Hi, I'm good. How are you? It's been
I'm brilliant.
fantastic watching all the movies.
Oh, I'm really enjoying this. Yeah, we're getting so many good questions and stuff from everyone watching. Tell us about your job, Pamela. What do you do?
So I'm an astronomer and I study the formation of stars, how to understand how they're born. I'm also part of the team that's going to be making sure that MIRI works as we expect it.
Cool. All right. So Ishael asked, they want to know what the telescope is going to look at first.
And that's a question that I'm just not allowed to answer. I don't know the answer to that one. They're keeping that a secret until we get to actual data taking. So like Tim mentioned earlier, we're going to spend the first 6 months making sure everything works. And then we're going to turn it loose on the sky and see everything from forming stars to the beginnings of the universe.
Oh my goodness. Yeah, we talked earlier about how Webb's going to show us newborn stars, like hidden behind clouds of dust, which I absolutely love, like this, from visible to infrared. But you just mentioned there that you're going to be looking back to the beginning of time. What do you mean by that?
So the light that we see from the sun was actually emitted 8 minutes ago. It takes light 8 minutes to get here. So just like if I were to get in a train and travel down to see my family in England, it would take me time to get there. Same thing with light, it takes time to travel. So we're seeing the sun 8 minutes ago, we're seeing the next star as it looked like 4 years ago, and we keep on going back in time as we look further through the universe.
Oh, I see. So because light doesn't just travel like that, it takes time to travel. It's a lot quicker than that, but because light takes time to travel, it takes 8 and a bit minutes for the light to get to us from the sun. So when we're looking at the sun now, the sun could like suddenly change color, but we wouldn't know for 8 minutes because it would take that long for the light to get to us.
Exactly.
And that therefore means that when you look further to something further and further away, it takes like longer to get to you. So you're almost looking back in time, which makes Webb a time machine.
Pretty cool.
Amazing. And also Webb's going to look closer to home as well, right?
Yeah, so we're also going to be able to do things like look at the planets in our solar system, Uranus and Neptune.
Okay,
Uranus
cool. Okay.
is tilted on its side, and we're going to see how that affects its seasons.
How fascinating. Okay, so we're going to be learning so much new stuff from this. I guess what I would like to know is what might it see? Like, and how long will it take for you to get that data?
So we're going to be looking at the planets, the stars, the galaxy, all the way out back to the beginning of the universe, what we call cosmic dawn, some of the first light ever emitted.
Oh,
and when we get that data, when we get those pictures, that's just the first step. After that, then we get to do all the cool science. We get to look at the images, we get to see the observations and understand what they're telling us about the universe.
And how many scientists are going to be using Webb for their research?
So over the whole lifetime of the mission, we're looking at thousands of astronomers are going to get to use the telescope.
And as you say, just getting the data is the first step for you. You're then going to have to like crunch all that data and work out what it means.
Exactly. It's going to take
How
a
exciting.
long time. So
I bet you can't wait.
I can't.
Thank you so much, Pamela. So great to chat to someone who's going to be using Webb to do some cool science. And I'll be keeping my eyes open for what you managed to see and work out. Thank you so much for joining us.
Take care, Greg.
Bye. I find Webb so inspiring. I mean, the engineering, the science, it's amazing. And it's not just me being inspired by the largest, most powerful space telescope ever to be launched, is it? Some of you lot have been very inspired too. So let's take a look at some more of your Webb-related arts and crafts, shall we? Yes, we shall. To do that, please welcome back, it's Jeremy again from the UK Space Agency. Hello, Jeremy.
Hi.
He did. So before you show us some more pictures, tell us a little bit more about the UK Space Agency.
Well, I guess everybody's got in their mind what NASA does. Imagine the same thing in the UK. We support research, so lots of areas in space, like supporting the Webb camera, for example, the Webb telescope. So we support missions that are looking at the universe, looking down at the Earth's surface and so on. But we're also helping industry by developing new technologies and making sure there's people with the skills needed by industry so that we can carry on doing what we do.
Talking of which, I know part of your job is working with youngsters who are interested in working in space. I know that a lot of these lot watching, I've seen it in the chat, a lot of these lot are inspired to maybe think about a job that they could have in the space sector, the area of all these different jobs. What would your advice be for them?
Well, we don't go into space just for the sake of it. We go to learn stuff. So whether it be trying to understand the universe, like with Webb, or whether we're trying to understand elsewhere in the solar system, we've got missions going to Mars and to Mercury, and even looking at the sun, and looking down at the Earth's surface to understand our environment and the climate and so on. So we're looking for people who can help solve problems, who can work in teams. Everything we do is collaborative, working in teams, so that's really important. So what I'd suggest is make sure you study science and technology or computing, because everything that comes back from space is pretty much computing information. So we need people from every part of the UK, every type of background, we're looking for a range of different people. So get stuck in.
There you go. Love it. All right, then let's have a look at some more of the people that have been getting stuck in. Have you got some more pickies for us?
Well, we've got about 100,000 people taking part in this country. So let's start with, this is Noelle's artwork. She's been working on NASA's Unfold the Universe campaign. And look at that. I think she's going to be an astronomer one day.
That's cool. That's probably inspired by the universe and what Webb might see.
Yeah. And then we've got Eleanor, who's drawn a picture of what she thinks she's going to see through her telescope. Another budding astronomer, I'd say.
Hang on. Is that the moon eating something? Cheese? Is that the moon eating cheese?
I like to think it's cake, but
cake. I mean, I always like to think it's cake. Okay, what else have we got?
Oh, right. Next, we've got Violetta. Now, she's been building a model with Lego. I just love Lego. I spent all my pocket money on that when I was little. But there's a video she's sent, so it doesn't just sit there. Let's see it work.
Oh, there it is.
It's
like a stop motion animation.
It opens up. I mean, we've seen how that operates. But
and the mirror opened up as well. That was so good. That was
brilliant.
Impressive. That was really impressive. Any more for us?
Yeah, we've got some people who've been learning about how Webb works so they can explain to other people. So these are actually astronomers. Even they need to understand it. And then we've got a brilliant selfie. Isn't that great? This is one of the deep space diary activities. Do you want to explain a bit more about that?
Well, that's really good because that's like the picture that that I made earlier.
It's exactly
right. So
yeah,
that's really cool.
Yeah.
Explain about the deep space diaries. Okay, so deep space diaries are something that a few of you might have been might have done at school, or if not, then you can get stuck in at home. So they are a do-it-yourself book of hands-on art and design activities about Webb. Schools have been working through them. If you want to try them online, they're free online. Try your hand at being a web engineer or a scientist, maybe over the holiday break. Any more?
I think we'll just end with last one.
Okay.
This is Threshter. She has made the most fantastic poster. I mean, that just covers everything, doesn't it? You've got
that's amazing.
There. I think that's brilliant.
And also, there's a web on there as well, which I think is super cool.
Great.
Jeremy, thank you so much for coming and talking us through it and telling us about all your work and mainly seeing these amazing pictures. It's super inspiring. If you lot have been excited and inspired about space, then I recommend checking out, you can check out your local astronomical society or your local science centre or your local planetarium. And again, there are more makes and experiments on the Webb UK website here at jwst.org.uk, and share what you get up to on Twitter, tag Webb Telescope UK. Nice. Thank you so much, Jeremy.
Thank
you. Appreciate it. Thanks for coming along. Well, you lot, it's pretty much time to wrap up this live mission briefing for the James Webb Space Telescope. If you are watching live, put your name in the live chat because I want to do a big round of goodbyes in a second. And if you're watching back, thank you so much for watching. What do we now know? So we know that the James Webb Space Telescope is the largest, most powerful telescope we've ever launched into space. It's got a massive gold-plated mirror, 3 times as tall as me, that will collect light from distant stars and planets. It's got 4 special scientific instruments on board that are like cameras, but they see not in the visible light, but with infrared light. And one is called MIRI, and that's going to be able to see through dusty clouds to see newborn stars inside. Webb is also going to be looking inside the atmospheres of our closer by planets, Neptune and Uranus. And Webb will see light from the very first stars and galaxies to help us figure out how they formed almost 14 billion years ago. We also know that Webb is currently folded up and attached to the rocket, the Ariane 5 rocket in French Guiana, ready for launch. If you're watching this live now, make sure you watch the launch live. It's scheduled now to launch on Christmas Eve, Friday the 24th of December. And I did see a comment from someone who says, maybe Santa might jump onto the rocket if it launches on Christmas Eve, which I absolutely love. So you can watch it here at ESA.int. Let's say goodbye to some of you watching live. I'll just do a handful. Goodbyes, Sam from Guardbridge, Benjamin, Jonathan from Kent, Jacob and Alice watching from Surrey, Robin, Evans, so many of you watching, thank you so much. And everyone who's watching back as well afterwards, thank you so much for joining the show. I can't end without doing some thank yous. So a big thank you to STFC, the Science and Technology Facilities Council, especially to Parker, to the Webb UK team, to Olivia and everyone there, to the UK Space Agency for supporting today's live mission briefing. A huge thank you to Raoul Space for welcoming us here to do the show, especially to Madeline. Thanks also to Vicky and Kate as well for your help. A massive thank you to Adrian and to Owen Salisbury for their help with the tech today. Owen's 18 and he's absolutely smashed it. A huge round of applause for Owen. Mega. Thank you to the Royal Observatory in Scotland for hosting some of my remote guests today. Super good. Thank you up there. And a big, big thank you to all of my guests, all of the scientists and engineers, the whole huge team involved in designing and building Webb. And finally, the biggest thank you to all of you watching. Let's have a look at our wide camera. It's a huge goodbye from all of us. Bye, everyone. Good luck on your adventures, Webb.